I'm Jeroen van Meij, and welcome to my lecture series on computer and network security. In this last video on asymmetric encryption, I will talk about digital signatures, which are arguably the most important application to have come out of this type of encryption algorithms. Digital signatures provide a set of security capabilities that would be very difficult to implement without use of public key cryptography. And here you can see a schematic representation of how digital signatures work. First of all, the sender takes the message M that he or she aims to transmit and provides it as input to a cryptographic hash function H. H generates a fixed length hash value out of this message. This message is then encrypted using the digital signature generation algorithm, which is a public key cryptography algorithm, using the sender's private key PRA. This encrypted hash value is used as a signature of the message M and is concatenated to the message before transmission. The receiver will then not only receive the message M, but also this signature. The receiver can verify the signature by taking a hash value of the message M and comparing that to the decrypted hash value of the signature. This hash value can be decrypted using the digital signature verification algorithm and the sender's public key, which can be obtained as it is publicly available. If the two are the same, the receiver knows that the message was not altered. Because let's say the message is altered by an attacker, this attacker would not be able to generate a valid signature as the attacker does not know the private key of the sender. And digital signatures are quite similar to authentication, which we already talked about in the past and can be done using, for example, message authentication codes, which also make use of cryptographic hash functions. However, message authentication codes only use a single private key, which is securely shared between the sender and the receiver. As such, a message authentication code allows verifying that the content of the message was not changed. However, a digital signature provides additional securities, and it ensures that anyone can verify that the message was indeed sent by the sender, because only the sender has access to the private key, but anyone else can obtain access to the public key and can thus verify the signature. When using message authentication codes, it protects the parties who exchange messages from third parties. However, it doesn't protect them from each other. To give you an example, let's say Mary and John exchange a message. Now, John uses a message authentication code to ensure the message is not altered in transit. However, since Mary also knows the private key that she shares with John, she could generate another message, create a message authentication code, and claim it comes from John. As such, John can always deny having sent the original message because Mary could create false messages. With digital signatures, this is no longer possible. Therefore, a digital signature must satisfy some properties. First, it should verify the author and time of the signature. Second, it should authenticate the contents at the time of creation of the signature. And third, it should be verifiable by third parties to resolve disputes. And this third property is very important and is not something that can be provided by message authentication codes. There are many different digital signature algorithms based on public key encryption, but let's take a look at one specific one called the RSA Probabilistic Signature Scheme, or RSA PSS, which is the latest of the RSA-based schemes and one that RSA Laboratories recommends as the most secure one. And here you can see how the signing and verification algorithms work in general terms. So, first on the left you can see the signing algorithm, where we start from the message M that we want to sign. We create an encoded message using some salt value. Then we take this message, which consists of a masked data block, a value H, and a value BC. This is also referred to as EM. Then we use the standard RSA algorithm with the private key of the sender, which is the one signing the message, to create the signature, which is basically the encrypted value of EM by taking EM to the power D modulo n. This signature S is then appended to the message when it is transmitted. On the verification side, which is performed by the receiver has the message M and the signature S. The receiver can then use the public key of the sender, which is E and N, to decrypt S into EM. EM consists of these three components and can then be compared to the same three components derived from the message M that was received to verify the signature. And let's take a look at how the message is encoded, so how EM is generated from the original message M. So we start from the message M, which is then given as input to a hash function, for example SHA-1, but any other hash function could be used as well, to create a hash of the message M. Moreover, we add some padding with 0 bits and a salt. This salt is a pseudo-random number that changes with every use of the signing algorithm for added security. This message M dash, which contains the padding, the hash value and the salt, is then sent again through the same hash function as before. This creates the final hash H. It's also used as input for the mask generation function and XORed with the value dB. dB contains padding, zeros followed by a 1, and also the same salt. This XORed value of dB is called masked dB and is appended at the front of the value EM. Then we have the hash value of our message and also a final value, hexadecimal value BC. The masked dB serves so that the receiver can actually retrieve the salt when decrypting the signature. And let's take a closer look at this mask generating function. The goal of this function is to generate some cryptographically secure pseudo-random bits that can be XORed with dB. The goal of the MGF is to create a variable length hash code using a fixed length hash function. For example, SHA-1 returns a fixed length value, but in our case we need a variable length output. So how does it work? Well, we start from our input to the hash function, our output T, which is initialized to an empty string, and a counter value initialized to 0. We then calculate the hash value, for example using SHA-1, of our input concatenated with our counter and concatenate that to the empty T. We then check the length of T, and if it is less than the desired length of the output, we repeat the same process but by increasing the counter K by 1. So again we calculate the hash value of X concatenated with the new value of K and concatenate that output to T. This is repeated until T is at least as long as the desired output length. Then we take the first L bits of T and return those as output. And this brings us to the final step of the RSA PSS digital signature algorithm. In this final step, I will show how signatures are verified. So the receiver will have access to the message M and also will be able to derive EM after using RSA to decrypt the signature. EM, recall, contains our masked dB value, our hash value from our original message M, and a constant hexadecimal value BC. The mask DB value can be combined with the MGF output of our hash value H using XOR to obtain our padding plus salt. We need this salt to calculate the verification hash value and ensure that it's the same as H. So the salt can be retrieved by using XOR, as the XOR operation is invertible. So then how do we verify if the hash of M equals the value H that was part of the signature? Well, we take the hash value of our message, which is M hash, in our M dash. We also add the salt and the original padding, and then take the hash value of this full message M dash. This hash value will be H dash, and the signature is valid if this H dash equals H. So this process allows the receiver to calculate the signature value H dash without actually having to separately receive the salt value, which is incorporated into the signature already. This salt value ensures that if a sender signs the same message M twice, the signature will be different every time, and thus it will make attacks on the signature much harder. And this concludes my videos on asymmetric encryption. In the next video series, I will talk about key distribution, or how to securely share both private and public keys between different parties. Thank you for watching.